I rather go to my slide and then started to discuss about the addressing mode. Addressing mode. So we started the addressing mode yesterday for both sections, all right? And we started with the introduction to a x86 type of instructions. x86 type of instruction supports 177 outputs. Output it has maximum two operand instruction and minimum no operand instruction. As you can see in the slide, MOV represents the opcode, operational code, where uh, it translates what you wanted to do. And we have two operands, data, most precisely you can say where does the data come from, where does the data come from. So basically you have a source operand and destination operand. Source operand is always on the left side, outer part of the instruction. This is followed by a semicolon and a comment. And kindly be informed that this format is only applicable when we wanted to write hardcore programs. Hardcore program. Then what is hardcore program? Hardcore program is typical assembly language, no notepad, no compiler is available. You write directly to the memory of the microprocessor. But when the environment changes, for example, by using MASM, Microsoft Assembler, or TSM, Turbo Assembler, or any other assemblers, which has compiler, notepad and compiler, where you can type your program and colorful messages pops up, then you cannot use this kind of instruction. So in that environment, you have to define uh, your variables. You have to define where does the program starts, where does the program ends, everything. Okay. So from here we go to what you call a register type of addressing mode. The type of addressing mode we have mentioned, there are three types of addressing mode. The first one is known as register addressing mode. Register addressing mode, in register addressing mode, both source operand and destination operands are registers. Both source operand and destination operands are registers. A typical example is move AX, BX, add AX, BX, increment AX, which is categorized under register addressing mode. We have some limitation for this addressing mode. Limitation number one is you cannot copy into instruction pointer, and you know why. Number two, if you wanted to copy to segment register, then only use general purpose registers, which are AX, BX, CX, and DX. Number three, you cannot copy an 8-bit number to a 16-bit number. And alternatively, you also cannot copy a 8-bit number to a 16-bit register. Both is not allowed in our BGC. Second matter is how am I going to calculate the physical address. You see, when in register addressing mode, if the data is part of the instruction, when data is part of the instruction, there is no step or stage of operand data calculation. Operand address calculation is not required over here. Operand operand address calculation is insignificant in or register operand addressing. Such you have to calculate only physical address for instruction or where does the instruction resides. Okay, so how do I calculate physical address for instruction in register operand addressing mode? Is by using CX, CS, and IP. CS 0 plus instruction pointer will give the physical address of 5-digit hexadecimal or 20-bit addresses where your instruction resides in memory. This is register operand addressing mode. Second type is known as immediate addressing mode. In immediate addressing mode, our source operand is a constant. Source operand uh, source operand is a constant. This is clearly to show us that we wanted to copy a number to any register. Okay, this is immediate addressing mode. And the same limitation applies. Number one, you cannot copy a number to a instruction pointer. Number two, you cannot copy a small number into a 16-bit register. Small number in this case is 8-bit number to a 16-bit register. And also you cannot copy a 16-bit number, sorry, you cannot copy a 16-bit number to 8-bit register, and similarly you cannot copy a 8-bit number to 16-bit register. Number three, definitely you cannot copy to segment register. You cannot set any segment register with any register you like to. If in case there is a need for us to set the data segment, extra segment, stack segment, or data segment, then we have to use general purpose registers as an mediator. Okay, so how do I calculate physical address in immediate addressing mode? Again, in immediate addressing mode, data is part of the instruction. Therefore, computing operand address calculation is not relevant over here. This leaving only physical address for instruction. And again, the calculation of physical address for instruction is same for all addressing modes. So what you have is CS0 plus IP, which will show you address to be fetched for next execution. So we have covered immediate and register addressing mode. Then the third one is how do we read and write from registers? Okay, in memory addressing mode, we have five different types of memory addressing mode. Uh, where the number one is the direct memory addressing mode. In direct memory addressing mode, we specify the addresses directly, like what has been shown on here. MOVCX square bracket 1, 2, 3, 4. Square bracket indicates that you wanted to copy from a memory address. Oh, shit energy. And also to be update with you that this square bracket is applicable for x86 Intel assembly language. Different microprocessor might have different way of specifying memory addresses. Okay, so you wanted to copy from memory 1234 into CX. When we talk about memory 1234, the second question that should come to mind is from which segment. We have code segment, data segment, extra segment, and stack segment. So definitely it is from the data segment because data segment has been allocated to store your data. Okay, and physical address calculation consists of two. Number one is to identify where your instruction has been stored in memory, and that is computed using the same method. CS and IP. IP is a representation of IP is a representation of offset over here, which will show you address to the next connect execution. Okay, that is known as instruction address calculation. The second step is once the instructions are being loaded into instruction queue, from instruction queue, this is the instruction will flow into control unit, and exactly in instruction decoder, it will be get translated and it will go into control unit, program control unit to generate microcode, the smallest microcode, also known as microprogramming, the smallest or the lowest programming translation that is available in any microprocessor. Then these microprograms will go into ALU for execution. Upon execution, the microprocessor will understand to copy DS1234 into CX. And now this is a 16-bit operation, although the memory is 8-bit. The memory is 8-bit, register given as 16-bit. So the system will copy memory location 1234 to CL and memory location 1235 into CH with total making CX. And the second physical address is physical address for data, which should be calculated from data segment and offset. Data segment DS is given as 200 as you can see over here, and offset is represented in the bracket 1234. So how do we calculate the address? 02000, put a 0 plus 1234, and you will end up with 03234. So the microprocessor will copy whatever inside here into CX. This is before and this is after. This example has been described in one of the classes, and two registers were given for you over here, that is data segment and AX. Instruction given as move to 7000 AX, and to confuse you, I can also give you code segment over here and ask you to calculate physical address for data. So physical address for data is calculated using data segment and offset. Over here, the offset is represented by 7000. The H indicate this is unit and hexadecimal. So you don't translate H into some other format in the exam. So how do I calculate physical address for the data segment 10,000? How do I get 10,000? We shift to the left and put 0 on the right side. This is arithmetic shift, and you plus with 7,000, so I get 17,000. Again, this is 16-bit instruction. So whatever inside AL will go into 17,000. Whatever inside AH will go into 17,001. This is exactly happening and shown in the diagram. Okay, you can use this as your example. You can work on this pattern. And we have the second type of instruction, addressing mode for memory, which is called register indirect addressing mode. Can you give me 1 minute? I'm going to take water. Please reply. I can't hear you. I don't know why I can't hear you. Is this because of the microprocessor damage, micro UFO handset damage, or my computer? Something wrong with the setting of the Google Classroom. Okay, let us continue. Can I continue? I can't hear you. Can I continue? Please reply in the group. How many people are still here? Out of 19 people, 90 people, we have only 45 people, 50% absent. The final exam paper has been submitted to the department. So we have four questions. Four questions. Normally I don't give four questions. I only have five questions. It is a mix between before midterm and after midterm. So one of the question is taken from the assignment. Assignment you're supposed to look at the assignments, look at the instruction cycle diagram, also look at whatever we had studied until today. Okay. Also the memory interfacing. I never had any file without memory interfacing. I would like to complete the memory interfacing. Let's see if we have time next week. We can complete it. Because whatever we have seen in chapter 5 is only 20% of what we're supposed to design memory interface. Okay, that is about our final exam. Let's go back to our memory addressing mode. Type 2 of memory addressing mode is register indirect addressing mode. Over here, we do not specify the addresses directly, but we point to the address by using a register. We point to the address by using the register. So the register acts as though it is a pointer. Acts as though it is a pointer. For example, uh, you wanted to write into 0100. So how do we write the program? Move AX comma open bracket 0100. Now we don't want to specify the address directly, but we wanted to point it out by using a register. So we say move AX comma 0100, and then we say move AX open bracket BX close bracket. How it is very simple. But not all registers you can use as a pointer register in register indirect addressing mode. Okay. The registers which is allowed is BX, SI, DI, and BP. Only four registers. If you try to use AX as a pointer register, then it is wrong. The system will not accept it. Will give you error immediately. Okay. So again, how do I calculate physical address? Number one, physical address for the instruction contained in code segment and IP. That is code segment shift to the left 0 plus instruction pointer. While the data is physical address for the instruction. Physical address for the data, you have to use this concept. Basically, it is DS data segment shift to the left for the 0. That's the meaning of multiply 10 data segment if you're using BX, SI, and DI. If you use BP, then we use stack segment. Why? Because BX, SI, and DI referring to data, while BP point to start of an array. Start of an array which is located in stack segment. The BP points to the starting of the array which is located in stack segment. It is very simple. If your pointing register is BX, SI, or DI, then use DS. If your pointing register is BP, then use SI. Example, this is example move AL comma open bracket close bracket BX. So BX become pointer register, and this is known as register indirect addressing mode, meaning to say that you are specifying the address indirectly by using a register. Okay, this is one of the examples. Another example for register indirect addressing mode. We have we were given DS as 0800 and we're given SI as 2000. Move the L comma open bracket close bracket SI, and this is 8-bit operation. Why this is 8-bit operation? Because you are using a 8-bit register DEL. How do I calculate my physical address for instruction? Physical address for the code, as usual, code segment plus IP. And how do I calculate physical address for data? It is very clear over here. I use data segment and SI. Data segment 0800. I put a 0 and plus with 2000. The SI is a representation of offset over here. SI is a representation of offset, and it is known as effective address. This address is known as effective address. How do we formulate the how do we formulate the uh, the what the offset is known as effective address. How do we formulate the offset is known as effective address, and effective address is only applicable in memory addressing mode. Okay, this is another example given move x comma si. So this is a 16-bit operation. Whatever in si, whatever address mounted by si will be copied to x. Whatever inside address pointed by si plus one will be copied to ah. Okay. Again, this is converted into binary code like 048B. It is located somewhere in the memory. So where is the somewhere is what we call physical address for the code, which is computed using code segment and IP. Again, the scenario repeats that the this is connected, address bus is connected to the memory, and everything happens. Whatever inside 0100 colon 000 will be read and put on address data bus. Data bus will take it to the instruction queue. From instruction queue, it will flow into control unit. From said control unit, it will go through decoder and control signal generator, and the microcode or microprogram generated will be fed into ALU. Upon executing this instruction, the system will know that you're supposed to read from DS02000 plus 1234 and put it into uh, whatever AX over here. Again, this is register indirect addressing mode. You can only use BX, BP, SI, and DI. If you use BX, SI, and DI to, to compute the physical address, we use data segment, and to compute physical address for data, if you use PP, then you use stack segment. Okay. Word operation. This is just uh, for you to exercise. So number three, we have base addressing mode. Base addressing mode. I give you 2 minutes or 1 minute for you to complete the notes. Okay, now let's restart with register addressing mode, and we are in the third category, which is known as base addressing mode. Base addressing mode is similar to register indirect addressing mode, but in addition, we have what we call displacement. It could be a positive displacement or a negative displacement. Positive displacement or a negative displacement. So the instruction looks like this: bx plus 10. This means do not take address in bx, but 10 unit above the address pointed by bx, or 10 unit below address pointed by bx. How should I say? Let's say that go to the coffee shop, but you don't want to go to the coffee shop, but go to the printing shop which is besides the coffee shop. Coffee shop is the referencing point, referencing register, but you wanted to go to printing shop actually. Same case over here. So what do you mean by over here is copy from bx 10 units after bx into cx. 10 unit after bx into cx. We also can specify the displacement inside the bracket or outside the bracket. It can be positive displacement or it can be a negative displacement. Example, move cx bx plus 10. Base move cx bx 10. If your bx is 0 1 0 0, then it does not mean that copy from 0 1 0 0, but copy from 0 1 0 0 plus 10. It could be a positive displacement or it could be a negative displacement. Okay. And question number one: how do I calculate physical address for instruction? Physical address for instruction is calculated using CS and IP as usual. How do I calculate physical address for the data? We use BX. Sorry, data segment. Data segment, put a 0 plus BX plus 10. Data segment, put a 0 plus bx plus 10. That's how we calculate physical address. Number one. Number two, in base addressing mode, base memory addressing mode, or whatever you want, we can only use bx and bp. This is this is when you compare with register indirect addressing mode, we can use bx, bp, si, and di. But in base addressing mode, we can only use bx and bp. And if you use bx, physical address is calculated using data segment. And if you use base pointer, physical address is calculated using a stack segment. For example, like what you see in front of you. Okay. Let's we have a exercise calculate PA for move bx plus 1 2 3 4. So the effective address is represented by bx plus 1 2 3 4. So how do I calculate my physical address for data? 0 1 0 0 0 1 0 0 for the 0 plus bx plus 1 2 3 4. So bx is not given over here. Bx is not given over here. So 0 1 0 0 plus plus BX plus 1234 is your physical address. Okay, this is another example. The operand field of instruction contain a base register BX or BP. This is what we mentioned, and followed by 8-bit constant displacement. 8-bit or 16-bit, it is acceptable. The displacement can be positive, the displacement can be negative. If the displacement is positive, it means you go to a higher address. If the displacement is negative, then you go beyond, you go to the back address. The example were given here, move x comma bx plus 4. You can mention it, you can mention the displacement inside the bracket or outside the bracket. It's up to you. Okay, so how do I calculate the physical address? The effective address is given by bx or bp. If the pointing register is bx, then we use data segment. If the referencing register is bp, then we use stack segment. This is what you call this is what we call effective address. Effective address represented by bx, bp, and displacement. So when we use cs, when you want to read data, when you want to read the code, when you use ds, when you're using bx, when you use ss, when you use bp. How about ds? Es also used when it's bx. But let's assume, let's take this method. This is much more dynamic. Okay, this is one good example. Move the X 1, 2, 3, 4 XL. So data segment is 0200. There are data segment 0200. Put a 0 plus BX. My BX is, what is my BX? My BX is 1000. So BX plus 1000. My displacement is 1, 2, 3, 4. So total we get 0, 4, 2, 3, 4. This is your physical address. And now if I ask you to calculate the effective address. Effective address is a 16-bit address. So we calculate bx plus 1, 2, 3, 4. Bx is 1000. So this 1, 2, 3, 4. 1000 plus 1, 2, 3, 4 is 2234. Is the effective address. Can you see the slide? I have moved to another slide.
Now I can see that, sir.
Can you see me? Are you following me? Are you following? Mr. Adib, Mr. Amirul, are you following me? Can you see the slides? Okay. Let's continue after this example. This is base addressing mode. So again, base addressing mode. How does the base addressing mode differ from register indirect addressing mode? Different number one, base addressing mode only uses BX and BP, while register indirect addressing mode uses BX, BP. Difference number two, base addressing mode must come with a displacement, while register indirect addressing mode does not come with a displacement. Let's go ahead. This is another example for you to work on. Move BX 1, 2, 3 for next instruction. This is another example for you to work on. BX plus 4. Okay, and number 5, this is fourth instruction. Fourth type under register in the register addressing mode. Sorry, fourth type in memory addressing mode. Fourth type. We will take our time until 10 o'clock, 1 hour. Okay, index addressing mode behaves same manner with base addressing mode, except for the register. Now we use SI and DI only. In index addressing mode, we use SI and DI only as a referencing register. And physical address for the code is computed using code segment plus IP, while physical address for the data is computed using data segment plus SI plus DI plus displacement. So displacement is a must in index addressing mode. So what is the difference between base addressing mode and index addressing mode is the uh, type of register we are using. We also can discuss from the point of view of application where we're needing how to use it in programming, but that will be a deeper study. Okay, so move dx si plus 5, move ci di plus 5, 20. These are the examples, and you can copy the physical address. The last one is known as base index addressing mode. Base index addressing mode. In base index addressing mode, this is base plus index. It means one of the register from base and one register from index must present. Number one. Number two, uh, displacement is optional over here. So the example is over here. I'm using Vx and I'm using Di. One from base addressing mode, another one from index addressing mode, and I have a positive 8 as my the displacement. The instruction can exist without displacement. So we use this in two-dimensional metrics. Assembly language. In assembly language, when we wanted to work on two-dimensional metrics, 2D matrix or 2D vector, we use this kind of instruction. So how do I calculate my physical address? It depends on the base addressing. If you use a BX, then I use data segment. If I use BP, then use stack segment plus DI plus 8. Okay, so DS shift to the left plus BX plus DI plus 8. So how do I write my effective address? BX plus DI plus 8. As simple as that. Can I make it bigger? So you can have a look at this. I use the data segment if the first register is BX, and I use stack segment if my first register is BP. So how do I calculate my effective address? BX plus SI plus displacement, if there is displacement. And note that I can't use BX and BP at the same time. I cannot use SI and DI at the same time. But one from base, one from index, and displacement is optional. Do I have examples? This is one of the examples, like move AH, BX, SI, 1, 2, 3, 4. So we use data segment. Is my data segment 0200, 0200 plus BX, 2000 plus BX, 1000, 3000, 3000 plus SI is another 2000, so 5000, 5000 plus 1, 2, 3, 4 is 6234 is my physical address in data segment. So we go to the system, we go to 06234, take BE and put into AH. This is 8-bit operation, so 062343235 will not happen. Only single operand, single memory will be copied to AH. So again, how do I get 06234? It's very easy. DS data segment 0200, put a 0, become 2000 plus BX is 1000, 2000 plus 1000 is 3000 plus SI is another 2000, 3000 plus 2000 is 5000, 5000 plus 1, 2, 3, 4, I get 6234. That is my address of the data located in data segment. Actually, I cannot call it 6000 because this is not in decimal. These are in hexadecimal, so I should call 6234. But to make things easy, I just call it 6000. Okay, this is for example given to you. Move SS equals to 2000, BP equals to 4000, SI equals to 800, A equals to 04. Calculate the physical address for data. So data is calculated by using SS, not DS. Why I'm using SS? Because my first This is BP. Therefore, I use stack segment. 20,000, how do I get 20,000? 2,000, put a zero, I get 20,000 plus BP. My BP is 4,000 plus SI. My SI is 800. So my physical address for data is located at 24,800 or 24800. Look at the instruction over here. The displacement is optional. Okay, this is displacement with basinage with displacement, where all these three format is acceptable, whether BX, DI, and 0200 separately, or use BX, DI, or if I mention like this, even I put DI first, BX, or 2010, these three format are applicable, but during the calculation of physical address, my which segment to use depends on the base address, base segment, whether B or BX or BB. Okay, this is the summary. This is the summary, and I will have to stop over here because I think I promised you 1 hour. Thank you very much for attending the class today. So one of these things are coming for your final exam. So please revise your addressing mode properly. Limitation, how to calculate code physical address, how to calculate data physical address, what is the limitation, examples of addressing modes. It should be coming out here. So can I log off now? Mr. Azim, Mr. Adib, Mr. Amir,
Which
please
um
reply.
yeah, sure.
Question to ask me, whether it's regarding the lab or regarding the class, we can spend a few more time to answer the question. Do you have any question, Mr. Adib? Mr. Amar? Yes, Mr. Daus. Hey, Mr. Daus, I think you were missing from the class. Okay. And also, please, those who have missed any quizzes in for the class or the lab, let me know immediately so we can have we can find a time to replace the lab quizzes. We'll reopen the iTalim if you miss the class quiz. Yes, Mr. Daus. What is the question? We have two groundwork. We just give interesting names so that you get attracted. Which one, Mr. Daus? The first one or the second one? The first one, you're supposed to show me a couple of tables. I forget how many tables. In the first table, that you're supposed to list registers of Intel 8080. So in the first table, you register the Intel registers in Intel microprocessors. You just compare a couple of them, like from maybe one example from 8-bit, 16-bit, 32-bit, and so on. Question number 2, you show the progress of cache with the year and what is the size of cache and name of the processor. Maybe you can attach or stick to only one type of processor. If you want to use ARM, just use ARM. If you want to use Intel, then use only Intel. Then only you will see the trend in the trend how the cache size changes. How many caches you have? L1, L2, L3 caches. Do I have L4 caches? I'm not sure. That's why I give you this assignment so that you will find latest information for us to understand. Number 3, I want you to show the DDR. DDR1, DDR2, DDR3, DDR4. What is the difference within this DDR? That
How
is
about the low power DDR as
basically
well?
that is the groundwork work. And if you have not submitted, please submit the soonest. You don't want to stress yourself during the last moment of your exam time. Okay? Because once I finish marking, I will not accept it. Question number two, groundwork number two. The microprocessor has gone through tremendous changes since its introduction in 1972. If you are referring to Intel microprocessor by introduction of 4004. Okay, so in this case, we have studied two things. One is the KPI evolution, and again, what we mean by KPI is a specification evolution. We have seen how it evolved from 4004 until Pentium 4. Number two, we have seen case study microarchitecture evolution. Okay, we also have seen system bus. We also have seen memory interface circuit. We also have seen the sizes. The sizes also evolved from 4-bit until 64-bit until today. So we want you to take one example of this, one example of evolution. Either it is in the whiteboard, it's in the whiteboard. Whether you wanted to take an example of instruction set and explain how the instruction set evolved, 1 to 2 pages only, not much. How the instruction set evolved from 4004 until Pentium 4 maybe, or until i3, whatever information that you could find with evidence. Oh, he said, no, I want to do micro architecture. The micro architecture is very easy. From single unit, it becomes multiple unit. Then you show the micro architectures changes with example and include pipelining in this. Okay. But please take only one type of microprocessor. You cannot mix all the types of microprocessor. I mean, you cannot mix Intel anyhow, and it will not lead you to anywhere. Okay, you just take one type of microprocessor, you analyze it, then you will see the changes. Or you want to talk about system bus, or you want to talk about memory controller, or you want to talk about clock speed. You take one of these and evaluate, yeah, elucidate, explain it further in the groundwork. Am I clear, Mr. Daus? It is best to have to do this assignment with a group because it might be a lot. Group. Any other question? Yeah, separate, separate. Or if you want to submit together, also can, no problem. I will make it separate so that you will get a better marks. Any other question? I'll be happy. Mr. Zenos, anything should be okay as long as I could see your work. I mean, like if you can show me that it's a progress, there's an evolution in the topic that you have selected, then it's okay. So I would like everyone to do this question. This is important effect on panorama. Point from also acceptable. It's same. You need to have a high level of English command to ready the same. Any other question? Please take the chance to ask the question because we are approaching the exam. Any other question, sisters? Or is everything? Mr. Zenos, everything starts from chapter one, numbering system. We never miss any question, any exam without asking about IEEE single precision. I do ask about IEEE double precision because basically the algorithm is same. So sometimes I'll ask you to convert a number to IEEE single precision format. Sometimes I'll ask you to convert find the decimal for given IEEE format. No question in pipelining. Sometimes I ask people to draw pipelining, construction pipelining, but whatever I give is very basic. So not worth of asking in final exam. We have a lot to study here because, as I mentioned in early classes, microprocessor is a subject of technical descriptive subject. Please ask more questions. Sisters, Nadratul Naib, where are you? Any other questions regarding the lab, regarding the class? For those who are in the lab, we will do assignment number lab number 5, and lab number 5 will be interfacing. How do we interface the microprocessor to external device? So that you will listen some speakers to make sound. You will see the LEDs is on, and there is no possibility for me to give you a quiz on that. So next week's lab quiz will be on shift and rotate instructions. Any questions, brothers and sisters? Okay. If there is no question from ladies and gentlemen, if there is no question from the floor, should I disconnect the Google Classroom?
Yes, sir.
Oh, someone is asking question. Can I compare LPDDR memory as well? Yes, yes, you can. It's just a table, Mr. Azim Rosli. Just a
Yes, I
table.
know.
Have you submitted
LPDDR is
your groundwork one? Groundwork, typical name.
because LPDDR
LPDDR.
is also part of DDR memory, right?
If you're not, you can compare LPDDR, no problem. Just a table, Just a table.
Okay, thank you.
Any other question regarding the lab, regarding the class? It will be 1st July, brothers and sisters. 1st July. When is the Hari Raya Haji? Abu Dhabi Haji is on Zulhijjah. So Zulhijjah is Jumaat number 1. 1st July. You start your Zulhijjah. You can fast for 10 days or 7 days. Don't forget to fast on Hari Arafah. Okay, so if there's no question, allow me to disconnect. Thank you very much for being here. I'll see you on Monday. Assalamualaikum.
Waalaikumsalam. Thank you, sir. Assalamualaikum.
Thank you,
Thank you.
sir.
Thank you, sir.
Thank you, sir.